Welcome to this presentation on the Distributed Randomness Beacon, DRB. DRB enables a group of N parties to collaboratively compute a public random output. The key features of DRB include its unpredictability, ensuring that future beacon outputs cannot be predicted, and its unbiasability, ensuring that no party can manipulate the output for personal gain. These qualities are crucial for ensuring fairness, security, and trustworthiness in generating public randomness. Unlike centralized solutions, DRB offers public verifiability, allowing anyone to verify the correctness of the random output without relying on a central authority. DRB finds applications in decentralized systems such as blockchain, lotteries, gaming, and decision-making protocols. In blockchain, it helps select proposers for new blocks, ensuring attackers cannot predict or manipulate the selection. Similarly, in decentralized lotteries, gaming, and decision-making protocols, DRB provides a reliable source of randomness, ensuring fairness and integrity in the processes. One of the ways to construct a distributed random beacon, DRB, is to employ the Distributed Variable Random Function, DVRF, a threshold cryptographic scheme characterized as a T out of N threshold scheme. In this setup, N parties are involved, but not all of them need to participate in the generation of randomness. Collaboration from only T parties is essential and sufficient. Typically, the threshold T is set as a majority of N, approximately half of the total. This configuration ensures system robustness, allowing for occasional node outages. DVRF is designed to achieve three vital security objectives: uniqueness, public verifiability, and pseudo-randomness. Uniqueness ensures that a public string X, whether a counter, timestamp, or block height, remains distinct throughout the system's operation. Consequently, the pseudo-random value V generated from X is unique and deterministic. This property is pivotal in applications such as selecting block proposers and validators, preventing undesirable forks in the consensus protocol. Public verifiability enables anyone to verify a cryptographic proof, ensuring the correct computation of the generated pseudo-random value, without relying on any central authority. Pseudo-randomness guarantees that the distribution of the pseudo-random value V appears indistinguishable from a uniformly random one, thwarting any attempts by attackers to discern patterns or biases. In essence, V appears entirely random to potential attackers. While alternative methods, like the traditional commit and reveal approach, exist for building DRBs, they come with shortcomings. For instance, the commit and reveal method, where nodes commit random seeds in one phase and reveal them in another, is susceptible to bias. If nodes perceive an advantage from the current output, they might withhold their committed seeds, leading to potential biases. Another approach, the verifiable delay function, VDF, mandates significant computational effort to recover the function output, introducing a delay to ensure unpredictability. This method, akin to proof of work, not only consumes excessive energy and electricity, but also poses challenges in controlling the required delay duration. DVRF, in contrast, avoids these issues, offering an efficient and robust solution for DRB construction. An innovative ZK-DVRF protocol has been under works, harnessing the power of threshold cryptography, ZK snarks, and BLS signatures. This new protocol consists of two integral components. The first, a non-interactive distributed key generation process, serves as the cornerstone. This phase orchestrates the computation of a global public key and individual verification keys for each node. These verification keys are made public, empowering each node with a corresponding secret key unique to them alone. Once the keys are established, the system seamlessly transitions into the generation of random output. Nodes execute partial evaluations, utilizing their secret keys, And when a requisite number of these evaluations, T, are accumulated, they are harmoniously amalgamated to produce the ultimate pseudo-random value. This meticulous process ensures a robust and secure foundation for the protocol's functionality. The NI-DKG process involves multiple distributed parties, each represented as a node. In this method, every node creates a secret random polynomial and utilizes it to calculate a public parameter. To ensure the accuracy of this computation, a SNARK proof is generated and published, typically on a blockchain or within a smart contract. These parameters and proofs can be transmitted within the contract, and upon successful verification, the public can confirm the validity of the zero-knowledge proof, ZKP. If they are valid, then the public can view the parameters in the generation of the global public key. Furthermore, the verification key for each node is accessible to the public. Consequently, every node can derive its own secret key using the publicly available parameters shared by other nodes. SK1 remains exclusive to the first node, SK2 to the second, and the public remains unaware of these secret keys. This setup establishes a non-interactive protocol where nodes generate and publish data just once, eliminating the need for continuous back-and-forth communication between them. After setting up the keys, random values can be generated for multiple rounds. Each round is identified by a public string, denoted as X. Using this X, every node employs its secret key to produce a partial evaluation through hashing X and applying its secret key, essentially performing scalar multiplication on an elliptic curve. This process also generates a cryptographic proof, demonstrating the correctness of the partial evaluation, akin to a signature, although it's a standard zero-knowledge proof and not a SNARK proof. These proofs are easy to generate and verify. Subsequently, nodes publish this data on-chain, such as within a smart contract. Notably, all N nodes are not required to generate partial evaluations due to the threshold scheme. Only T nodes are needed. Once T-valid partial evaluations are obtained, they can be utilized to compute the final pseudo-random value. To compute the value, we begin by obtaining the value pi, calculated through a combination of partial evaluations from the T-nodes using Lagrange interpolation. This pi is unique and deterministic because the variable x is fixed in this context. Additionally, there exists a fixed secret key called GSK, corresponding to the global public key, and it is the result of a secret key generation process during the non-interactive DKG process. This GSK is unique, and no one possesses its value as it is implicitly generated. Once we obtain the value of pi, we then hash it again to produce the final random value, V. This second hashing step is essential to ensure that the distribution of V is indistinguishable from a truly random value. This property is crucial for the security proof, demonstrating the pseudo-randomness of V. The SNARK proof technique utilized in non-interactive DKG is implemented within Halo 2, a zero-knowledge proof system in the style of Planck. A performance evaluation has been conducted on an AWS instance equipped with 32 CPUs and 256 GB of memory, representing a moderate computational load. One crucial parameter in this evaluation is the circuit degree, which determines the maximum number of gates supported in the computation. For instance, with a circuit degree of 18, the system can accommodate up to 2 to 18 gates, enabling support for a maximum of 9 nodes in the DKG protocol. Alternatively, with a degree of 19, the system can handle up to 2 to 19 gates, allowing for a maximum of 21 nodes in the protocol. The SNARK proving time increases linearly with the number of nodes, such as 20 seconds for 9 nodes and 40 seconds for 21 nodes. Verification takes 5.7 milliseconds, but slightly more as nodes increase due to additional public inputs. To address this, hashing public inputs can reduce verification times. Snark-proof size remains constant regardless of nodes. Peak memory usage aligns with the size of n. Randomness generation is quick, 0.8 milliseconds for partial evaluation and 1 millisecond for verification. The combine function scales linearly with the threshold size, measured in milliseconds. Combining partial evaluations can be done off-chain, while the verification of the final pseudo-random value, which takes a constant 1.6 milliseconds, can be performed on-chain. This process is open to anyone and doesn't involve secret information or keys. The next project step involves integrating with Optimism's leader election using DVRF. Optimism currently uses Espresso's round-robin algorithm for validators. This DVRF can randomly select validators for slots, improving the security of the process. The RANDAO contract, Ethereum's random number generator, is being considered for integration. Unlike RANDAO's three-phase approach, DVRF omits the first phase, using partial evaluations submitted by nodes in the second phase. Verification in the third phase ensures the final pseudo-random value's validity. Additionally, components for non-interactive DKG, including smart contracts for snark-proof verification and global public parameter computation, are under development. Thank you.